Testing, testing, 1, 2, 3. So we're gonna do the second problem here now. And you can just read it as I'm just gonna paste it in here. So you see the word, so you can pause, read it. You see the word salt. Salt means there is two, I guess, atoms or molecules attached to each other, and they are ionically attracted to one another. So you have two atoms or molecules ionically attracted to each other, which means one of the atoms gave an electron to the other atom or molecule. Let's say NaCl. Na gave its electron to Cl. So now Cl has extra electron, and Na has, one less electron, right? And so there is an attraction because Na is kind of attracted to the electrons that chlorine has, is like the theory, and the electrons of chlorine, are attracted to Na. Particularly Na's nucleus. The protons in Na are attracted to the electrons, but no matter what, no matter. So Na is attracted to Cl because of the donation of the electron. So that's a salt. BaSO4 is, let's see. So you have a soluble barium salt. So some salts are soluble, which means that they dissolve in water. And all it wants you to know is that this salt dissolved in water, and when it dissolves in water, like let's say it's NaCl, the Na will be no longer attracted to the Cl. It's like separated from it, but it's still lost its electron. It doesn't gain it back. So we're gonna signify that with a plus, and Cl still has the electron. We'll signify that with a minus, and that's what happened here. Now let's say you had NaCl, and I can't think of a good example, so I'm just gonna use X, Y. Okay. And the same thing happened with X and Y. It was soluble, so it dissolved when placed in water. So you had X plus and Y minus. Now, since they're separated from one another, it's very easy actually. Sometimes the Na will come back to the Cl. Or maybe the Na will come to the Y, because the Y has the same attractions that the Cl had. It has the extra electron. So Na is going to be attracted to the Y minus. But let's say this happens, and this ends up being not soluble. So this was soluble when the Na was attracted to the Cl, but this is actually not soluble. So it stays this way. It's not going to separate again. So you might have this sort of start to collect on the bottom of the beaker, instead of it just dissolved, now you can see it. Like Na still lacks an electron, Y has an electron, so they're attracted to one another still, just like Na and Cl was. It doesn't matter that Y has someone else's electron. These are all the same electrons. So this is exactly the same sort of attraction as this, but this is probably maybe stronger, or not that actually. It's, well, maybe. I'm unsure. Before I explain too many things at once. So yeah. So you have this, it forms, and because it forms and it stays formed, and these aren't separated from one another, you're gonna begin to see it. I guess. So instead of yeah, so it's gonna like form. I'll explain more about this in a later video, like, you know, why you can see it form as a solid is there's just a little, quite a bit more to know, but it's still very straightforward. This whole thing is very much straightforward in terms of why you can see it, why all this happens, why you can just collect this and such. Mainly because these don't separate from one another anymore. Na can go back to forming with Cl, but it'll just separate again. Once it you know, hits the Y, once this particle runs into this particle while in water, it will stay that way. So back to this question. So you have 10 grams of barium salt. So Ba Y. I know barium is going to be losing its electron out of prior knowledge that you will have, and so it's gonna be treated with an excess of sodium sulfate. So sodium sulfate, and yeah, so both of these are gonna dissolve in water. And I know they're gonna be like dissolved in water, not just because it's like one, it says they're both salts. Two, it precipitates something, which means like the Ba had to separate from the Y. This had to separate from the SO4. Again, they're both salts, so I assume they separated, and this came with this. Precipitate means form a solid, essentially, from this type of reaction. That's just what it means. So this precipitated out. This precipitated out. That's just what it means. So that's probably the biggest thing, obviously. The fact that it precipitated out. So yes. Which barium salt is it? So this question will get us into, well, now we can get into, okay, what makes something soluble? That's what it's really asking. It says it's soluble. This whole thing about the 10 grams, the 11.21 grams, I don't think... Oh, it might be relevant. This might be a harder question than I think it is. But first, let's see which one of these is soluble. So and then we can go from there. That's the main part of the question that I'd like to teach, or like kind of explain. So what's soluble here? We need to look at a table. That'll tell us. We're not supposed to memorize it, but we should have some intuition, some sort of ability to, like, guess pretty well if something's soluble or not. It just will make things easier. Don't look at the answer. No, okay. Let's see. It doesn't... So, they are a little bit more advanced than AP. AP will have the, yeah, they'll have the table. These, like, they expect you to memorize this, which is pretty surprising. Like, my first guess would be this, just because I know that NO3 is just, I think it's always soluble, but I'm unsure. But Mr. Voss has one of the, well, he takes the AP one, which is smart. Has one of the equation sheets. I guess it's an equation sheet. I mainly want the solubility table. Yeah, a lot of equations. Oh. I mean, not very many. Like, I don't even know. Like, I might have used this on the test. I don't even remember using this on the test. I might have. But it's mainly just knowing which formulas to like kind of use. Like if I had to use this, I would have a really good idea of where I'd be looking. You just would. Let's see if I can just find one of the things that I need. Mr. Voss has this. I just can't find it. Yeah, I think these are called solubility rules. Seems just, yeah, I guess, yeah. Yeah, okay. So, yeah. This is okay, I guess. Like, I don't expect them to be wrong. This one looks fine, actually. Yeah, NO3 is always soluble. So that's why I was like, probably the NO3 one, because it's just always soluble. And we know that it's soluble. I think there might be multiple solutions here that are soluble, though. So that would make that, not... Yeah, Cl. Cl is also soluble. Because it says it's soluble except one with Ag, one with silver, mercury, and lead. And this is barium. So that means that it is soluble, because it's not one of these, That's just chart reading. So yeah, so this is soluble, bromine isn't listed here. So the bromine's also soluble. I doubt the I would call it whatever, the OCH2. Let me see if there's even that. I don't even know if that could be soluble. O2CH2. O2. Oh, O2CH2. O2. So that one is a... So I might just pretend that every choice they gave me was soluble. It just is seeming that way. Well, I don't need to put... I just need to think of if there's one. I don't even yet. I might just pretend it's soluble just because I can't really find it. O2C. Yeah. So I'm just gonna pretend it's soluble because, So this is actually not a question about solubility rules. It's a question about being big-brained. We have 11 point. It's about these numbers they give us. They're actually relevant. So M. I'm pretty sure that's... Wait, that's a little weird. You see, because M is typically, so this probably means molar mass. I can just make sure of that by... So let me calculate the molar mass to make sure that's what M means. Because M can mean something else as well, but they italicized it. That's like the difference, I guess. But... So let's see. So I'm going to take the molar mass of this, barium sulfate, and see if it matches this number. BaSO4. So I need a periodic table. I think the Chem Olympiad sheet actually just has this. 137.3. I don't actually, let's not use a calculator because that's not the big brain thing to do, you know, kinda, Okay, so 137, so BaSO4, okay, so we have Ba, so 137.3, O4, that's gonna be 64, 64 plus that is 201.3 plus, so 233.07, and there's just, I mean, I think I did that, like, kind of correctly, at least. Oh, 0.37, whoopsies, I just guess I didn't add this correctly. So yeah, that would be, so it matches, because I got 233.37, and that's 233.4, they just rounded, so yeah, that means molar mass. So yeah, because it's pretty basic just to, I guess, like, calculate molar mass, so they just don't want you doing that. They don't want you to waste your time with it. So yeah, that's what this italicized M means. M, just normal M, can mean something else that we will find out later. So we have, 10 grams of soluble barium. And it's going to precipitate this much barium sulfate. So we're trying to find, I guess, So this is an interesting question. I think there's multiple ways you can do this. So essentially it's like saying, okay, so this is 11.21 grams, and you had 10 grams of barium attached to something. It's like you're trying to, I guess, balance like this sort of metrics. So I'm going to just do something simple. I'm going to figure out how many barium atoms there are here. I think that's just the most logical way. I'll do it two different ways. One way that I was kind of more just thinking, which should get you the same answer. And another way that's more logical, I guess. So, okay. And this is going to be stoichiometry. So, we have 11.21 grams of barium sulfate. We know the molar mass. We know the molar mass is 233.4. So that means for every, so that means there are 233.4 grams of barium sulfate per mole of it. Okay? So when I say, like, make sure you're making sense, like, you have 11 grams of barium sulfate. If there's 233 grams per mole, that means when you do this calculation, you're probably going to get like a small number because you don't even have a mole. You have less than this. So like that's like something I try to think, like when I'm doing the calculations, just like mentally checking, this should be a lower number after I do the calculation because there's 233 grams per mole. I only have 11 grams, so thus I don't have many moles. 233 grams per 1 mole. I only have 11. So, but, you know, when I do this, I would probably just try also just canceling out units. So 244 grams per mole. So grams divided by grams is nothing. You're dividing by 1 over mole, so that's, you're getting it on top. If that makes sense. It kinda-ish does to me. like in terms of, I don't know how logical it is the way they teach that sort of bit. So you have, or at least not intuitive. So you have 0.048, and you only have to like round this because all these answers should be pretty distant from each other. Although I have the bad habit of like if there's a 0, I just stop there. It's not very, I guess, very accurate, I guess, or very reliable. So yeah, you have 0.048 moles of barium sulfate. Which means you have, so sometimes they'll be like, okay, so you have 0.048 moles of barium sulfate, and this is going to be relevant to answering this question when I do this little problem. How many moles of oxygen are there? Well, there's 0.048 moles of this molecule. That means, well, there's 4 oxygens per molecule. So it's like, there's 0.048 moles of this molecule. You have to multiply that by 4 to get how many moles of oxygen there are. So, you know, there's 0. You know, 1. It doesn't matter. It doesn't matter because, you know, you just multiply that by 4 and you get your answer, right? So back to the question, though. So 0.048 moles of barium sulfate. That means you had 0.048 moles, or how many moles of barium would you have? Well, there's 1 barium per molecule, so it's as if you just had 0.048 moles of barium. Now, you need an answer choice, I guess, where if you had 10 grams, and I'm not going to start branching from here. I'm just going to continue from this calculation, I feel, because I'm not going to confuse you like that. I don't want to, at least, because that's confusing. It's already confusing for me, or for anyone who would do this. Just in general, it's going to be confusing. So you have 10 grams, right, of Ba and something else. I'm not going to put a Y because that's an actual element, I now realize. I don't know. X. Oh, no, I had... maybe, like... I don't know. No. Okay. Unknown. Sure. N. N-A. Okay. There we go. The best... yeah, no. Okay. So, we have 10 grams, right, of this mystery salt. We have barium, oopsies, attached to something. Now, actually, I do see a way you could do it from here. It might be even easier. But, essentially, you're asking yourself, okay, which calculation would get me this having 0.048 moles of barium? Because if you have a very heavy element here, then that means like you don't have very many molecules of barium. Because I mean you don't have very many molecules of this. If this is like really heavy, but if this is like really light, then you have like you could have a lot of molecules of this because this is just based off weight. So you know if this is 1 gram, well that's really heavy. But let's just say this is 1 gram. Well, you need 10. You'll have 10 of these. But if this is 5 grams, then you only have 2 of these. So you're trying to get, okay, which one will get you 0.048 moles of barium? So you're kind of wondering, okay, 10 grams, well, okay. So 0.048 moles of barium times what? Will get you, I guess, 10 grams. You're gonna... okay. That's... okay. I'm going to just do it how I'm gonna do multiple ways of this, I think. So, yeah. So, I'm thinking, okay, well... so, you have let's assume for like this, okay? Every single time you have one barium molecule. I mean, one barium atom per molecule. So if you multiplied, I guess, the molar mass by, if you multiplied this by the molar mass, you should get 10 grams. Because, think about it, you have 0.048 moles of barium, which means you have 0.048 moles of barium and whatever, you know? You have that many moles of barium, whatever. So, because again, you have that many moles of barium, there's only one barium per molecule, so you have that many moles of barium attached to whatever. And the molar mass of this element, you know, how many grams per mole, needs to end up getting you a number that's 10 grams. You know, once you convert this into, you know, what's the mass of it, you should get 10 grams. So you can actually just be like, okay, maybe, you know, well, you could just, this is just algebra at this point, really, because you're like, okay, 10, this times what equals 10? 10, okay, so you just be like 10 divided by this equals that. And, or you could just plug in random numbers, but, you know, you want to get it as fast as possible, so I will divide.